The saying "nothing comes from nothing" is well known. Applying this to a galactic context raises the fascinating question: how could the universe literally arise from nothing? For earthly life, something can only form if the necessary components exist. But where did the material come from that made the birth of the cosmos possible? We'll delve into this profound question, exploring expert opinions and the limitations of our current understanding. The Planck epoch, in the very early universe, is a key area of investigation. This is before the formation of stable matter, even protons and neutrons. Revolutionary discoveries continue to reshape our understanding of the universe's deepest mysteries. The Big Bang, Big Crunch, and Big Freeze theories, while differing in details, share a common endpoint: the end of the universe. Eventually, the last star will burn out, leaving a bleak void. Giant black holes will consume remaining matter before eventually evaporating, marking the ultimate act of destruction. Space will expand until even the faint light from these evaporating gravitational behemoths becomes too diffuse to interact, bringing cosmic activity to a complete standstill. While many researchers view this as the final end, some propose it's a new beginning. Some scientists believe such a dark, cold, empty universe was the precursor to the Big Bang. This necessitates further investigation into the origin of the first physical matter. To explain the emergence of stable matter, atoms and molecules, we must acknowledge that nothing like this existed during or immediately following the Big Bang. We know that the first atoms formed from simpler particles as conditions cooled. We also understand how these atoms later fused in stars, creating heavier elements. However, our current understanding doesn't explain how something arises from nothing. Tracing back further, protons and neutrons, the building blocks of atomic nuclei, are considered the first long-lived matter particles. These are thought to have formed immediately after the Big Bang. Before that, no matter existed in the classical sense. However, physics allows us to probe even further back, before the emergence of stable matter, into the Planck epoch. In physics, this era is described by grand unified theories. These posit that during the Big Bang, three of the four fundamental forces, strong, weak, and electromagnetic, were unified into a single force. Deeper into this speculative area, the physical world was a soup of short-lived elementary particles, including quarks and electrons. Matter and antimatter existed in a near balance. Every matter particle had a near-identical antimatter counterpart. If these particles, differing only in a single aspect, collided, they annihilated each other. Quantum field theory suggests that even a vacuum, considered empty space, teems with activity, featuring energy fluctuations that can create particles that quickly disappear. Thus, the spacetime vacuum itself also exhibits these particle creation and annihilation events. This further pushes the question: how did spacetime itself arise? The Planck epoch demonstrates the limits of our current physical theories. This extremely brief epoch immediately followed the Big Bang, when space and time themselves were part of quantum fluctuations. A complete theory of quantum gravity, unifying quantum physics and relativity, is needed. M-theory and loop quantum gravity are promising candidates. Here, space and time are considered emergent. What we perceive as space and time is a result of quantum processes at an incredibly small scale. Because our usual understanding of space and time breaks down in the Planck epoch, our classical concept of cause and effect also reaches its limits. Theories describe some kind of physical reality that existed then, a quantum precursor to space and time. While causality may not apply, it's theoretically possible to understand one component of the Planck epoch through another. However, current theories cannot achieve this. Until comprehensive theories are developed, we can't make well-founded statements about the formative processes of the cosmos. Currently, physicists know of no confirmed instance of something arising from nothing. Creator, multiverse, or cyclical models are therefore considered. Because deciphering the quantum state of the universe at the beginning of the Planck epoch is impossible, all theories remain highly speculative. Some invoke a divine creator. Others, less religiously oriented, consider a multiverse as the most promising approach. Our cosmos is just one tiny link in an endless chain of other universes. Related theories suggest a continuous cycle of destruction and rebirth. This is supported by Roger Penrose's conformal cyclic cosmology. Penrose found striking mathematical parallels between the Big Bang and the distant future of the universe. They are almost identical when taken to their limits. This led to the paradoxical hypothesis that the complete absence of matter gave rise to all matter in the cosmos. The Big Bang, therefore, arises from something close to nothing. The remnant after the universe's matter was annihilated by black holes, which subsequently decay into photons. How can a cold, empty universe correspond to a hot, dense one? Mathematically, this involves conformal scaling, a geometric transformation that changes an object's size but leaves its shape intact. The shape of the universe's space in these two states can be made to coincide. In other words, the hot, dense state arises from the cold, empty state. Thus, the end of an expanding cosmos is followed by a new Big Bang. Even if Penrose's theory is confirmed, questions remain. How does physical reality arise? How was a cyclical universe formed? Why is there something rather than nothing? Can nothing, the absence of everything, even exist? These are philosophical questions. We'll maintain a focus on physics. One approach suggests there may be no physical explanation, perhaps an infinite chain of repeating cycles where the initial quantum state of each cosmos determines the properties of the next. Alternatively, there might be only one cycle, where the beginning is determined by the end. The vast uncertainty makes the topic compelling.